So hopefully by now you've seen the PA equals LU lesson. The punchline there is that we can row reduce A to row echelon form U, and along the way we can concurrently build the lower triangular matrix L and the permutation matrix P. PA equals LU allows you to do all sorts of things. For example, you can figure out the rank of A by figuring out the rank of U. And you can take any system, AX equals B, and chunk it into easier systems, LY equals PB, and UX equals Y. Now, Sage has the capability to figure out PA equals LU, but the defaults aren't quite the way we've done things. So I just want to point out a few things here. So the syntax for an LU factorization is A.LU, open parentheses, and there are these things called pivoting strategies that certain algorithms use. We have used a pivoting strategy called the non-zero pivoting strategy. What this means is that when we search for pivots, we don't care what they are, we just want something that's not zero. There are other pivoting strategies that are optimized to reduce rounding errors. So one is called what's called maximal partial pivoting, where you use the largest possible number to create a pivot because that reduces rounding errors down the road. So there are different pivoting strategies, but the one we're using is called non-zero. Okay, so if you issue this command, Sage will spit out P, L, and U, but the P it spits out is the transpose of the P we're working with, and the U it spits out is not necessarily in row echelon form. It's only upper triangular, so we might have to actually take a few extra steps to get to row echelon form. So I've input the example that I did at the end of lecture as a default here to see how this works. So the matrix that I've input on the first line is exactly the matrix from lecture here. So it's this A. And then down here, I'm defining P, L, and U according to the appropriate syntax for an LU factorization in Sage. And then I'm redefining P as its transpose because that's how we are presenting things in class. And now the print statements will tell me A, P, L, and U. So let's see what happens when I evaluate. So here's what spits out. So remember, the A matrix we're using here is the same as the A matrix from class. And the idea in our algorithm is that we reduce A until we get to U. Now, one thing I want everyone to pay attention to here is that the U we're getting is actually not in row echelon form, but it's really close. So U here is upper triangular, but it's not in row echelon form. So you'll see that like the last row here has a bunch of zeros and then an 8, and then a bunch of zeros, a 5, and a negative 15. That was what we got in the second to last step of our row reductions. So if you look at what Sage is spitting out, Sage is spitting out the state of U, L, and P at the second to last step because Sage is content to just get to upper triangular, but we want to get to row echelon form, so we had to take an extra step here. So you can use this calculator if you want a PA equals LU factorization to get maybe all the way if it just so happens that you get to upper triangular as soon as you get to row echelon form, or you might have a few extra steps at the end. But this gets you most of the way. But it is cool because you can see here that the P that we got to here is the same as the P at this stage of the algorithm, although we had one more row swap to go, so that's actually not the same P that we ended with when we did our algorithm. And the L that we got is exactly the L that we would have gotten if we terminated the algorithm at the second to last step, but we needed one more row swap to get to our final stage. So this gets you pretty far, but not necessarily all the way.